A few years ago, NASA was studying old photos of the moon when something strange caught the scientists' attention. What appeared to be just a dark shadow on the surface was actually the entrance to a huge cave hidden beneath the lunar ground. This cave is so big that an entire city could fit inside it. For billions of years, this hole sat there, waiting to be found. Scientists were shocked because this changes everything we thought about the moon. Could there be hundreds of other hidden caves that we still don't know about? Get ready to fall asleep while listening to this video and discover the secrets the moon has kept for so long. Subscribe to the channel, leave your like and comment where in the world you're watching from, get comfortable and relax. Let's begin. Imagine stumbling upon a hidden city not by launching a new rocket, but by squinting at a picture in your family album you've seen 1,000 times. Are there more entrances? What does the floor look like? Answering those questions will ironically require new missions, rovers, landers, and perhaps penetrators. But those missions are now being designed with a specific, confident target in mind, all because of a second look at an old photo. The financial and logistical efficiency is staggering. Without this archival work, we might have eventually stumbled upon such a feature, but it would have been through blind luck or an expensive, dedicated survey. Instead, we have a roadmap derived from existing assets. This model is being applied elsewhere. On Mars, scientists are constantly re-examining data from the Curiosity rover's old traverse paths, or from orbital missions like MRO, finding new evidence for ancient water or mineral deposits that were missed initially. The principle is universal. The data holds more stories than the first draft of analysis can reveal. In a very real sense, the discovery bridges past and future. It honors the legacy of the missions that collected the data, often from previous generations of scientists and engineers, and it directly informs the ambitions of the next generation planning to live and work on the moon. It validates the painstaking work of data archivists and curators who maintain these vast digital libraries. For the public, it's a thrilling narrative, treasure found not in a faraway land but in the attic. It makes the process of science feel accessible and cumulative. You don't always need a new telescope. Sometimes you just need a new thought. As we move forward, this case study will undoubtedly be cited in proposals and textbooks as a prime example of cost-effective discovery. It will encourage funding for data analysis projects alongside flashy new hardware. The cultural shift within space science is already happening, with a greater emphasis on long-term data analysis grants and interdisciplinary teams that include computer scientists and data miners alongside geologists and astronomers. The lunar skylight is more than a geological feature. It's a symbol of a smarter, more sustainable way to explore. It proves that our first waves of reconnaissance, often seen as preliminary, can contain the keys to our future footholds. So the next time you hear about a new discovery on an ancient world, remember that it might not have required a launch. It might have required a click, a new line of code, and a researcher willing to doubt that everything in the old photo had already been seen. The greatest discoveries are indeed often hidden in plain sight, waiting for us to develop the right gaze. This particular gaze was digital, patient, and brilliantly retrospective, turning the past into a portal for the future. The volcanic maria cover about 16% of the moon's near side, a vast area. It is statistically almost impossible that the single skylight we've been discussing is the only one. Scientists are now actively hunting for more, applying the same image analysis techniques to other likely regions. They're looking for those telltale clusters of pits, or alignments of depressions that might trace the subsurface path of a tube. Every new entrance discovered would be a new target, a new potential site for scientific treasure or a future base. Understanding the geology of these tubes is the essential first step in every subsequent discussion about them. You cannot talk about exploring them, using them, or protecting them without first understanding what they are, how they formed, and what their inherent properties and risks might be. This foundational knowledge informs the engineering challenges of accessing them, the scientific priorities for the first robotic probes, and the long-term vision for human settlement. The lava tube is not just a hole, it is the product of a specific and violent chapter in lunar history, a chapter that physically shaped the world we see today. Its formation is a story of incredible heat meeting incredible cold, of fluid dynamics playing out in a low-gravity vacuum, and of the patient, billion-year-long preservation that only a world without an atmosphere can provide. This geology transforms the moon from a two-dimensional landscape into a three-dimensional world with a hidden layer, a subsurface realm that is now a primary target for 21st century exploration. The discovery of the skylight was the breakthrough, but the real story begins with understanding the fiery river that carved the tunnel in the first place, a river that stopped flowing billions of years ago but left behind a cavity that will shape our future in space. Understanding that these are lava tubes carved by ancient rivers of fire immediately leads us to the next mind-bending question. Just how big are they? When scientists and engineers talk about a single cavern potentially housing an entire city, it's not a vague metaphor or science fiction hype. It's a direct conclusion drawn from physical models, radar observations, and the fundamental principles of geology in a low-gravity environment. The scale is not just large, it is monumental, redefining what we consider possible for a natural structure and fundamentally altering the blueprint for future human presence on the Moon. Let's put some real dimensions on this idea. On Earth, the most impressive lava tubes like those in Hawaii or the Canary Islands might reach 30 or maybe 50 meters in width, big enough to walk through, even drive a small vehicle through, but still fundamentally a tunnel. The lunar data tells a completely different story. Estimates derived from the size of the collapsed skylight openings, the topography of the surface above suspected tubes, and specialized radar that can probe a little below the surface all point to structures of a different order of magnitude. We are talking about stable widths that could easily span 300, 500, even 1,000 meters. That is not a tunnel, that is a cavern with a ceiling so high and distant it might feel like an underground sky. In terms of length, these tubes could run for tens of kilometers, tracing the paths of the ancient lava flows that created them. The reason for this colossal scale boils down to two main factors we touched on earlier but need to fully appreciate: gravity and preservation. The Moon's gravity is 1/6 of Earth's. This has a profound effect on structural engineering, even natural structural engineering. The stability of an arch or a ceiling is critically dependent on the weight of the material itself. On Earth, the immense weight of rock over a large span causes it to eventually fracture and collapse under its own load. On the Moon, that same rock weighs 6 times less. The forces trying to pull the roof down are dramatically weaker. This means a lava tube roof on the Moon can be orders of magnitude wider and still remain standing over geologic time. The physics models are clear. What would be an impossible, unstable cavern on Earth is a perfectly viable, permanent fixture on the Moon. The second factor is the lack of degradation. Without weather, water, or tectonic activity to wear it down, a tube that formed 3 billion years ago remains almost exactly as it was the day the last lava drained out, save for a slow sprinkling of impact debris. So, these aren't just potentially big, they're reliably, permanently big. Now, let's translate those dimensions into a mental image. A width of 500 meters is more than 5 American football fields placed side by side. The height from the floor to the ceiling could be on a similar scale, perhaps 100 meters or more. That volume is staggering. You could fit multiple large skyscrapers lying on their sides inside that single continuous space. You could have separate zones for living quarters, agricultural modules, scientific laboratories, manufacturing hubs, and storage depots, all within one shielded, connected environment. The concept of a city becomes a practical architectural consideration rather than a poetic one. This scale changes everything for habitat design. On the surface, every module is precious, cramped, and needs to be heavily shielded, leading to designs that are often compared to submarines or bunkers, functional but inherently confined. Inside a cavern of this size, you could think differently. You could erect large, perhaps even inflatable structures that don't need to withstand micrometeorite impacts or radiation shielding in their walls, because the cavern itself provides that. You could create open spaces, communal areas with a sense of physical and psychological spaciousness that is impossible in a clustered surface base. You could have vertical infrastructure using the height for storage lofts or elevated walkways. The cavern provides a natural, prefabricated superstructure. It's the ultimate fixer-upper. The walls, floor and ceiling are already there, stable and protected. Our job would be to outfit it, not to build the shell from scratch. This plug-and-play real estate is arguably the most valuable terrain on the Moon. Furthermore, this immense scale offers fantastic operational advantages. The sheer volume provides a massive buffer of stable, cool temperature. It offers immense space for radiation shielding. You could even pile up regolith on top of your habitat modules, asterisk inside asterisk, a cavern for an extra layer of safety without the complexity of doing it on the outside in a spacesuit. Logistics become easier when you have room to maneuver, store, and organise. Imagine a landing pad on the surface near the skylight entrance, with cargo and personnel being lowered down into a vast warehouse-like receiving area. From there, electric rovers could transport goods along smooth, predefined paths within the tube to different districts of the base. The tube itself could act as a natural roadway, protecting travel from the harsh surface environment. The economic implications are just as profound. Scale enables industry. If you discover valuable resources like water ice or specific minerals within the tube, you have the space to set up processing plants without the constraints of a tiny surface outpost. You could pilot large-scale manufacturing, like using lunar regolith for 3D printing construction materials in a controlled, spacious environment. This isn't just a base, it's a potential industrial park. The psychological impact on crew members cannot be overstated either. Long-duration space missions grapple with the issue of confinement and monotony. A habitat buried in a small surface module where every wall is a hard boundary and the outside is a lethal vacuum exacerbates these issues. A habitat within a colossal cavern, even if the human-built part is still modest, provides a profound sense of place. The cavern itself becomes a landscape to explore, a geological feature to study, a tangible connection to the moon's history. The mind can perceive it as a place, not just a pod. This sense of spaciousness and environmental variety is a priceless asset for crew health and morale on missions that could last months or years. It also presents unique scientific opportunities at this scale. The vast, protected interior might have its own microenvironment. Volatiles released from the rock over eons might have collected in cold traps in shadowed sections of the tube, far from the entrance. The pattern of debris on the floor, the stratification in the walls, the thermal gradients across such a large space. All of these are data points that tell the story of the moon's past. Exploring a space this large requires new approaches. Robotic rovers would need advanced autonomy and mapping capabilities to navigate what is essentially a new frontier, a dark, alien continent sealed underground. The sheer size means that initial explorations could focus on one small section near an entrance for years before we ever fully map the entire length of a major tube. This scale also suggests connectivity. If one tube is this large, it's possible that networks exist, with smaller tubes branching off from main trunks, creating a veritable subway system of empty volcanic conduits. Mapping this potential labyrinth becomes a primary scientific and exploratory goal. Of course, this monumental scale comes with its own set of challenges and questions. How do we confirm the dimensions remotely before we send anything down? How structurally sound is a ceiling that wide over billions of years? Could there be partial collapses deeper inside that we can't see from the entrance? These are engineering puzzles that need solving. But the foundational point remains, the discovery isn't of a cave, it's of asterisk realm asterisk. It shifts our thinking from building small, isolated outposts on an alien surface to potentially settling into a prepared, spacious, and protective niche within that alien world. The lunar surface is the frontier, but these tubes represent the potential for a home within that frontier. The data suggests spaces so vast they challenge our earthbound intuition for what a cave can be. This isn't a hole in the ground, it's a subsurface arena. It redefines the very architecture of planetary settlement, suggesting that the most practical way to live on a hostile world might not be to armour ourselves against it on the surface, but to move into the spacious, ready-made shelters it formed for itself billions of years ago. The promise of that scale is what transforms the discovery from a fascinating geological footnote into the central pillar of a sustainable lunar future. It provides the physical volume necessary to dream bigger, to plan for permanence, and to envision a human presence on the moon that is not merely surviving, but thriving in an environment that, for all its alien nature, offers a staggering gift of space. All that incredible city-sized space inside a lunar lava tube isn't just a real estate perk, it is the cornerstone of its ultimate value as a sanctuary. The cavern's monumental scale is impressive, but its true transformative power lies in what its walls and ceiling prevent from getting inside. The surface of the moon is one of the most hostile environments a human could ever attempt to inhabit. a brutal landscape of extremes that demands a fortress-like approach to survival. Moving operations into one of these subterranean voids isn't just about gaining room, it's about acquiring a pre-built near-perfect shield against every primary threat the lunar surface throws at us. Let's break down exactly what we're being shielded from, because it makes the case for caves overwhelming. The first and most insidious danger is radiation. On Earth, we are protected by a thick atmosphere and a global magnetic field that deflects and absorbs charged particles from the sun and deep space. The Moon has neither. Its surface is bathed in a continuous deadly stream of galactic cosmic rays, high-energy particles from distant supernovae, and is periodically blasted by intense solar particle events from our own Sun. This radiation doesn't just pose a long-term cancer risk, it can cause acute radiation sickness, damage sensitive electronics, and even degrade the materials of habitats over time. On the surface, the only solution is to build shielding, which means either hauling enormous amounts of material from Earth or developing complex technology to pile meters-thick layers of lunar regolith on top of every habitat. It's a massive, constant engineering burden. Inside a lava tube, you get that shielding for free. Several meters of solid basalt rock overhead act as an incredibly effective radiation barrier, reducing exposure to near-Earth background levels or even lower. The rock absorbs and breaks apart those high-energy particles, creating a safe, quiet environment underneath. It is the ultimate form of passive protection, a geological bunker that never requires maintenance or reinforcement against this particular threat. The second major hazard is the wild temperature swings. A lunar day lasts about 2 Earth weeks, and during that long afternoon, surface temperatures can soar to 260 degrees Fahrenheit. The following 2-week night plunges those same rocks to 280 degrees below zero. This 300-plus degree swing is a nightmare for engineering. Materials expand and contract, seals are stressed, and maintaining a comfortable internal temperature for a habitat requires immense amounts of energy for heating and cooling. Thermal control systems become large, complex, and single points of failure. Inside a cave, the environment is thermally pristine. The rock acts as a magnificent insulator, dampening those extremes to almost nothing. Just a few meters in from the entrance, the temperature stabilizes at a steady, constant freeze, somewhere around -20 to -30 degrees Fahrenheit, determined by the Moon's own internal geothermal heat flow. While still very cold, this stability is a gift. Engineers now have to design for one predictable, constant temperature rather than two wildly opposing extremes. Heating a habitat from a steady -25 degrees is far simpler and less energy intensive than cooling it from 260 degrees one day and heating it from -280 the next. The thermal management systems can be smaller, more efficient, and far more reliable. The third clear and present danger is micrometeorites. The Moon's surface is constantly being sandblasted by tiny particles of space dust, travelling at speeds many times faster than a bullet. Over millions of years, this process grinds the surface into fine regolith. But for a human habitat, even a tiny puncture from a grain of sand-sized particle can be catastrophic, causing a slow pressure leak. Surface habitats require multiple layers of Whipple shields, specialised bumpers, to vaporize these particles on impact, adding weight, complexity, and cost. A lava tube's roof, which may be tens of meters thick, has already taken this punishment for billions of years. It is our primary meteorite shield. Any particle that might pose a threat is stopped long before it reaches the interior void. Inside the cave, the risk of a micrometeorite strike on a habitat is essentially zero. This allows for lighter, simpler habitat wall designs, potentially even using inflatable structures that would be far too vulnerable on the surface. The protection extends beyond just these three big ones. The cave also eliminates the problem of lunar dust in its most hazardous form. On the surface, the regolith is electrostatically charged by solar radiation and is incredibly abrasive and clingy. It gets into everything, jamming mechanisms, damaging seals, and posing a serious respiratory hazard if tracked into a habitat. The dust inside a cave, while still present, is likely to be different. Shielded from the solar wind that charges it, it might be less electrostatically sticky. Furthermore, it has not been gardened by billions of years of impacts in the same way. It might consist more of coarse debris from the ceiling and walls, rather than the fine razor-sharp powder of the surface. This could make it a more manageable problem. There's also a psychological dimension to this shielding, living on the surface with the knowledge that a thin wall is all that separates you from a lethal vacuum, intense radiation, and a constant pelting of micrometeorites contributes to a sense of vulnerability. Being inside a solid mountain of rock, with meters of protection in every direction, provides a profound sense of security and permanence that a surface module cannot match. This shelter effect is primal and would undoubtedly benefit crew morale on long-duration missions. From a pure engineering and risk management perspective, using a lava tube is what's known as a massively leveraged solution. Instead of solving each problem, radiation, thermal swings, micrometeorites, with separate, heavy, energy-intensive and fallible active systems, you use one single geological feature to solve them all simultaneously, passively and permanently. It reduces the mass you need to launch from Earth, the power you need to generate on the Moon, and the number of systems that can fail. It simplifies the entire architecture of a lunar base. This isn't just an improvement, it's a paradigm shift in how we approach planetary habitation. We stop trying to replicate Earth's protective bubble through technology alone, and instead co-opt the natural structures of the other world to achieve the same result. It's the difference between building a wooden hut in the middle of a hurricane and finding a strong dry cave in the side of a mountain. One is a constant fight against the elements. The other is a strategic use of the landscape for innate resilience. Of course, the cave environment introduces its own set of challenges. Absolute darkness, potential structural instability, and access logistics. But these are arguably more tractable and familiar engineering problems than the fundamental relentless hostility of the surface. We know how to generate light, we know how to reinforce rock walls, we can develop elevator or ramp systems for access. We do not, however, have a cheap, lightweight and perfectly reliable way to cancel out cosmic radiation or stop the thermal cycling of metal from 260 degrees to minus 280 every 2 weeks. The trade-off is overwhelmingly in favour of the cave. This protective quality also preserves any scientific value inside the tube. Just as it shields humans, it has shielded the interior geology from solar wind alteration and cosmic ray bombardment for eons, making it a pristine scientific site. And for any long-term vision of industrial activity, the stable, protected environment is ideal for precision manufacturing and sensitive equipment that would be compromised by the surface's wild fluctuations and radiation. In essence, the lava tube transforms the problem of lunar habitation from a defensive struggle for survival into a more manageable task of interior outfitting and systems maintenance. It provides the ultimate safe zone, allowing effort and resources to be focused on exploration, science and expansion, rather than perpetually reinforcing the walls against a deadly outside. This intrinsic, multi-layered protection is why these discoveries have ignited such excitement. They aren't just interesting geological features, they are the closest thing the Moon offers to a ready-made move-in condition home, turning a mission profile from surviving at the surface into thriving underground. That incredible protective quality of the lunar cave does more than just safeguard future astronauts. It has, for billions of years, safeguarded the Moon's own ancient secrets. How fast did it flow? The texture of the rock, the size of crystals, the presence of bubbles or vesicles, tells us about the lava's viscosity and gas content as it solidified. This is a level of detail about lunar volcanism we have never had access to. Every single mission to the Moon's surface has collected samples that were, to some degree, weather-beaten. The cave offers the textbook page before it was left out in the rain. Then there is the mind-bending possibility of volatiles. Volatiles are substances that easily turn to gas, like water, carbon dioxide, ammonia, or methane. The surface of the Moon, in direct sunlight and vacuum, is terrible at holding on to these. They either bounce off or get broken apart by radiation. But in the permanent shadow and cold stability of a deep cave, especially in areas far from any skylight, they could have found a permanent trap. Imagine comets or water-rich asteroids impacting the Moon over the ages. Some of the material they throw up could, by chance, end up drifting into a cave opening and settling in a cold, dark corner where it remains frozen for billions of years. This isn't just water ice. It could be a cocktail of primitive compounds from the early solar system. Finding a deposit of such volatiles inside a non-polar cave would be a scientific bonanza. It would tell us about the delivery of water and organic materials to the Earth-Moon system long after its formation. The samples would be pristine, uncontaminated by solar radiation, making them perfect for analysis. But the implications stretch even beyond the Moon itself. The Moon is essentially a museum for Earth's early history. Its surface preserves a record of asteroid impacts that has been wiped clean on Earth by weather and plate tectonics. A sealed cave environment could take that a step further. It might preserve a record of the solar wind and cosmic ray flux over billions of years in its untouched soil layers. It could trap ancient gases from the Moon's own outgassing, or even, speculatively, traces of Earth's early atmosphere if material was exchanged during giant impacts. Studying this environment is like being granted access to a laboratory that has been running a 3 billion year experiment in planetary preservation. Each layer of dust on the floor, each mineral coating on the wall, each potentially icy patch in the dark is a data point in a story we have only heard fragments of. This scientific value dictates how we must approach the first missions. It creates a tension between exploration and preservation. The very first robot to enter that cave will be contaminating it, however slightly, with earthly microbes or molecules. This makes planetary protection a top priority. Probes will need to be sterilized with a rigor approaching that used for missions to Mars, because the goal is to study a pristine environment, not one we've smudged with our own fingerprints. The protocols for sampling will be incredibly careful, designed to distinguish what is native from what we've brought with us. This turns the robotic explorer into a sort of archaeological field worker, documenting the context of every scoop and scan. The scientific investigation would be systematic. First, a mapping phase, using lasers and radar to create a detailed three-dimensional map of the entire cavern, noting every bulge, crevice and debris pile. Then a survey phase, using spectrometers to scan the walls from a distance, identifying mineral compositions and hunting for spectral signatures of water or other ices. Finally, the sampling phase. A rover would carefully approach chosen sites, perhaps using a drill to extract core samples from the wall, or a scoop to collect sealed samples of the floor material. These samples would be the crown jewels of planetary science, potentially more revealing than any since the first Apollo rocks. They would allow us to calibrate our entire understanding of lunar geology. We could finally know, with precision, what the ground truth is, against which we can compare all our remote observations of the Moon and other planets. It would settle debates about the Moon's thermal evolution, the timing of its volcanic periods, and the nature of its mantle. Furthermore, by comparing the pristine cave samples with the gardened surface samples, we could precisely quantify the effects of space weathering, a process important for understanding the surfaces of asteroids, Mercury, and other airless bodies. In a very real sense, this single cave could become the Rosetta Stone for airless world geology. Its value isn't just in what it tells us about the Moon, but in the key it provides for interpreting data from missions across the solar system. The pursuit of this knowledge will drive the design of the most sophisticated robotic explorers we have ever built, demanding new levels of autonomy, sterility, and analytical capability. The cave, as a geological time capsule, presents the purest form of the scientific imperative to seek an untainted record of the past. It promises a clarity of understanding that the battered surface can no longer provide, making it not just a strategic haven for humanity, but a pilgrimage site for science. The drive to uncover this preserved history will be as powerful as the drive to find shelter, ensuring that the first entities to truly inhabit these spaces will be our most careful and curious machines, sent to read the pages of a story that stopped being written before multicellular life arose on Earth. That pristine scientific record inside the cave is of incredible value, but let's be brutally practical for a moment. There is one specific substance that, if found within those dark, protected recesses, would instantly catapult these geological curiosities to the top of the lunar priority list, overshadowing almost every other consideration. That substance is water. The search for accessible, mineable water ice is not just another science objective. It is the holy grail, the game changer, the single most important resource we could possibly find on the Moon. Everything about a sustainable, long-term human presence expands from this one point. Think about what water means in space. It is not just for drinking, it is the foundational resource for life support, allowing for closed-loop systems where water is recycled for consumption and hygiene. More critically, through a well-established process called electrolysis, you can split water into its two component parts, hydrogen and oxygen. Oxygen is obviously for breathing. Hydrogen combined with that oxygen is rocket fuel. So in one package you have the essentials for keeping humans alive and the propellant to get them back home or launch them onward to Mars. This is what's called living off the land or using in situ resources. The economic implications are staggering. Launching anything from Earth is astronomically expensive, costing tens of thousands of dollars per pound to get it to the lunar surface. If you have to launch all the water and fuel for a mission from Earth, your mission is severely limited in duration and scope. But if you can mine your water and manufacture your fuel on the Moon, you break the logistical chain to Earth. You enable permanence. Now we know water exists on the Moon. Orbital missions have definitively detected the signature of water ice, but it's almost entirely in a very specific, very challenging place. The permanently shadowed craters at the lunar poles. These are some of the coldest places in the entire solar system, where sunlight never reaches, allowing ice to survive for billions of years. But these locations are brutally difficult to operate in. They are freezing beyond comprehension. They are dark and they're often located in rugged, difficult terrain. Setting up a mining outpost there would be a monumental engineering challenge. This is where the caves come in. The question scientists are urgently asking is, could there be secondary deposits of water ice asterisk inside asterisk, these lava tubes at more temperate mid-latitudes? The theory is compelling. Over the Moon's long history, water molecules from comet impacts or solar wind interaction could have migrated across the surface. When they encounter the cold trap of a permanently shadowed polar crater, they stick. But a deep, dark cave, especially one with a constricted entrance that limits sunlight, could also act as a very effective cold trap. The interior, shielded from the sun, would maintain a stable, frigid temperature. Water molecules that bounced or migrated into the cave entrance could lose their energy and freeze onto the coldest surfaces in the darkest corners, far from any skylight. They would then be protected from sublimation, a process where ice turns directly to gas in a vacuum. The cave becomes a natural freezer. This isn't just about water either. Other volatile compounds like ammonia, methane or carbon dioxide could also be trapped there. These are all incredibly useful resources. Ammonia could be a source of nitrogen for plant growth in habitats or for chemical processes. Methane could be another fuel source. Finding a mix of these volatiles would be like stumbling upon a stocked pantry. The search for this potential resource will define the early robotic missions to these caves. The first rover or lander sent to a skylight will carry sensitive spectrometers and neutron detectors pointed not just at the surface, but down into the abyss. They will look for the telltale signs of hydrogen, which indicates water. If they get a strong signal, the next mission becomes a mining prospector. How would we actually extract it? Imagine a robotic lander positioned near the skylight. We could lower a specialized rover or a drilling platform down into the cave. This machine would navigate to the darkest, coldest section of the floor, likely near a wall or in a deep recess. There, it would use a drill or excavator to dig into the regolith. If ice is present, it would likely be mixed with dirt, forming a kind of frozen concrete. The robot would then need to process this material, probably using heat. A simple oven could bake the soil, releasing the water vapour, which would then be captured on a cold plate or condenser, where it would refreeze as pure ice. This harvested ice would then be stored in insulated tanks. It's a straightforward process in concept, but a massive challenge in the reality of a dark, dusty, unknown cave. The machinery would need to be fully autonomous, robust, and capable of operating for months or years. The potential payoff, however, justifies the effort. A successful ice mine inside a protective cave creates a powerful synergy. You have the shelter asterisk and asterisk, the resource in the same location. This transforms a base from an import-dependent outpost into a potential hub. It could become a refueling station. Spacecraft from Earth could land with minimal fuel, refill their tanks using locally produced propellant, and then launch to other destinations in cislunar space or beyond with a fraction of the initial mass from Earth. This makes the entire economics of lunar and deep space exploration more feasible. For the astronauts living there, water means sustainability. It means the ability to grow plants in hydroponic bays using recycled water and lunar soil. It means a buffer of life support that allows for larger crews and longer stays. It also provides a radiation shield. Water is an excellent absorber of cosmic rays, so storing it in tanks around habitats adds another layer of protection. The psychological impact of having a plentiful, recyclable water supply is also huge. It moves the mission from a feeling of precarious scarcity to one of established abundance. The search for this cave ice is therefore a two-tiered investigation. The first tier is pure science, understanding the distribution and history of volatiles on the moon. The second tier is applied human survival, finding the gas station and the well for our future expansion. It bridges the gap between exploration and settlement. If the polar ice deposits are the vast remote oil fields, then cave ice deposits would be the conveniently located natural springs. Their accessibility and co-location with prime real estate make them uniquely valuable. This quest will drive innovation in robotics, in situ resource utilization technology, and subsurface exploration techniques. It will force us to develop systems that can not only find the water, but also sustainably manage it. The discovery of even a modestly sized deposit would trigger a new gold rush, not for gold, but for the most precious commodity in the cosmos, the chemical combination of 2 hydrogen atoms and 1 oxygen atom. It would mark the moment the moon transitioned from a destination to a home base. So, while the cave's protective qualities and scientific archive are compelling, the whispered promise of water is what gives the exploration of these voids its most urgent and exciting thrust. It transforms the narrative from one of mere survival in a shelter to one of thriving through self-sufficiency. Every mission plan for lunar caves will have this question at its core: is the water there? The answer will determine the pace and ambition of everything that follows, making the search for volatiles the central economic and existential drama of the next phase of lunar exploration. The potential for water and the profound scientific secrets are what draw us to these caves, but before a single human ever sets foot near one, we have a massive, purely mechanical problem to solve. How do we actually get in there? How do we explore an environment that is perpetually dark, incredibly rugged, and completely cut off from direct communication? The answer is that our first pioneers will not be human. They will be robots, and designing them for this specific task is one of the most fascinating engineering challenges in all of space exploration today. Think about the very first obstacle, the entrance. That skylight is a hole in the ground, often with sheer vertical or overhanging walls that could be tens of meters deep. You cannot just drive a standard rover up to the edge and roll in. The approach is a cliff, so the first generation of cave robots will need to be expert climbers or adept at controlled descent. Concepts for this are varied and ingenious. One idea is a mother rover that stations itself securely at the rim. This rover would act as a base station for power and communication, and it would deploy a smaller exploration rover on a tether, lowering it like a climber on a rope into the darkness. This tethered approach solves several problems at once. It provides a physical link for power and data, and it allows for a controlled retrieval of the smaller robot. But it also creates limitations. The exploring rover can only go as far as the tether allows, and that tether can get snagged on jagged rocks. Another concept is a robot built like a spider or an insect, with multiple legs and grippers that could carefully climb down the rough wall of the skylight. This requires incredible mechanical complexity and software to navigate such an unpredictable surface. A third, more speculative idea involves jumping or flying robots. The moon's low gravity makes flying more feasible than on Earth, but the cave is an enclosed space with no atmosphere, so propellers are useless. Instead, you might use small thrusters, like a miniature rocket pack, to hop from ledge to ledge or to fly directly down. This is energy intensive and risky, as a wrong move could slam the robot into a wall. The most likely near-term solution is the tethered descent from a stable lander or large rover, because it gives the most control for that critical first step into the void. Once inside, a new set of challenges awaits. The most immediate is absolute darkness. There is no ambient light. The robot will need to bring its own and not just a simple headlamp. Effective exploration requires lighting systems that can illuminate wide areas for cameras and also specific focus beams for detailed inspection. More importantly, the robot needs to see in 3 dimensions to navigate. This is where LiDAR becomes essential. LiDAR works by firing millions of laser pulses and measuring the time it takes for them to bounce back, creating a precise 3D map of the surroundings in real time. This map is crucial for the robot to understand where it can and cannot drive, to identify interesting features like layered walls or potential ice patches, and to not drive off a ledge or into a deep crevasse. The robot will essentially be building a map of a place no one has ever seen from scratch as it goes. This leads directly to the next huge challenge: communication. Radio waves do not travel through rock. Once the robot descends below the rim of the skylight, direct communication with Earth or even with the surface lander is lost. The signal is blocked. Therefore, the robot must have a high degree of autonomy. It cannot wait 20 minutes for an engineer on Earth to see a problem and send a command to turn left. It has to make its own decisions about path planning, hazard avoidance, and even when to stop and conduct science measurements. We are talking about artificial intelligence and machine vision software far more advanced than what powers today's Mars rovers, which still rely heavily on daily instruction uploads from Earth. To maintain a link, one solution is to deploy a string of communication nodes, like breadcrumbs. The mother rover at the surface could lower a radio repeater down just inside the entrance. The cave robot could then deploy further repeaters as it ventures deeper, creating a daisy-chain network that relays signals back to the surface. These nodes would need their own power, likely small batteries, and would have to survive the cold. Another approach is to use very low-frequency waves that might penetrate some rock, but that would mean slow, low-bandwidth data transfer, unsuitable for streaming high-definition video or complex LiDAR maps. So, a hybrid approach is probable. High autonomy for the robot to operate independently for hours or days, with periodic returns to a zone where it can establish a strong link to upload its data trove and receive new, broad objective commands. The terrain inside is another unknown. The floor is not going to be a smooth parking lot. It will be littered with boulders that have fallen from the ceiling, cracked and tilted slabs of lava, and potentially deep pits or cracks. The robot's mobility system must handle this. Tracks like those on bulldozers or some Mars rovers provide good traction and distribute weight. Wheels are simpler but can get stuck more easily. The multi-legged walker concept is highly adaptable but mechanically complex and slower. Whatever the design, it must be incredibly robust. There is no repair shop. A single broken actuator or a wheel jammed by a sharp rock could end the mission. Redundancy is key. Multiple motors, backup systems for critical functions. Power is also a constant constraint. Solar power is impossible in the dark. The robot would need batteries and perhaps a radioactive power source like a small radioisotope thermoelectric generator which provides steady power from the decay of plutonium. This is heavy and involves safety protocols, but it offers long-term reliable energy independent of sunlight. All these systems, lights, computers, motors, heaters to keep electronics from freezing, draw a lot of power, so energy management is a core part of the mission design. Finally, the robot must carry its scientific toolkit. This includes the LiDAR and cameras for mapping, but also contact instruments. A robotic arm with a drill or abrada to scrape rock samples, spectrometers to analyse the chemical composition of the walls and floor. Perhaps a small oven to heat samples and sniff for volatile gases. All this instrumentation adds weight and complexity. Each mission will have to prioritise: is this scout primarily a mapper, a geologist, or a prospector looking for water? The first one will almost certainly be a mapper and general surveyor, tasked with answering the basic questions. How big is it? What is the shape? What is the general makeup of the floor and walls? Is there any visible ice? The data from that first scout will then inform the design of the next, more specialised robot. This technological development is not just for the Moon. The systems created for exploring lunar caves have direct parallels on Earth. Think of robots for searching collapsed mines after disasters, or for inspecting unstable tunnels. The autonomy software for navigating without GPS in complex 3D environments is applicable to underwater exploration, or for robots working in hazardous industrial sites. And of course, it is a direct test run for exploring the far larger and more significant lava tubes we suspect exist on Mars. A successful lunar cave robot is a prototype for the machine that might one day descend into a Martian cavern in search of signs of past life or future shelter. So, while the vision of human cities in the Moon is captivating, the immediate and equally thrilling story is the engineering puzzle of getting a smart, tough, and independent machine down into that darkness and back out with the knowledge we need. It is a field of robotics pushing the very boundaries of autonomy, mobility, and resilience. Every solution invented for this problem brings us closer not only to understanding the lunar underworld, but to mastering the tools for robotic exploration anywhere. The robot will go first, as it must, braving the absolute dark and unknown terrain so that we can finally see what has been hidden for billions of years. Its success or failure will write the first chapter of practical lunar cave exploration, determining the pace and possibility of everything that comes after. Those robotic explorers we send down first will have a primary mission of mapping, prospecting for water, and assessing the geology. But there is a quiet, profound question that will be in the back of every scientist's mind as they look at the data. Could these caves, sealed away for so long, contain any trace of the building blocks of life? Now let's be perfectly clear from the outset. No one is seriously expecting to find little green men or even bacteria living in a lunar cave. The moon is almost certainly sterile, but sterility does not mean a complete absence of organic chemistry. The discovery of such a perfectly preserved environment reopens, in a very serious and scientific way, a fascinating line of inquiry related to something called panspermia and the study of prebiotic chemistry. Panspermia is the hypothesis that the basic ingredients for life, or even very simple life itself, could be spread between planets and moons by meteoroids, asteroids and comets. It suggests that life on Earth might have gotten a kickstart from the materials delivered from space. Whether you buy into that idea or not, we know for a fact that space is not empty of organic matter. Meteorites called carbonaceous chondrites, which are some of the most primitive materials in the solar system, are packed with amino acids and other complex organic compounds. For billions of years, the moon has been bombarded by this stuff. On the surface, it's a dead end. Any delicate organic molecules that land there are quickly destroyed by the relentless solar ultraviolet radiation, the constant barrage of cosmic rays, and the wild temperature swings. The surface is a terrible place to preserve fragile carbon-based chemistry. But inside a cave? That's a different story. Imagine a comet rich in water and organics slamming into the moon. The impact would vaporize and throw ejecta high and far. Some of that ejected cloud, containing water vapor and organic compounds, could by chance drift into the open maw of a skylight. Inside, in the permanent darkness and stable cold, those molecules could settle onto the cold cave floor or condense onto dust grains. Shielded from the destructive radiation that ravages the surface, they could just sit there for billions of years. The cave becomes a natural freezer, a cosmic storage locker for some of the oldest chemical ingredients in the solar system. This possibility transforms a lunar cave from a geological site into an astrobiological one. The goal wouldn't be to find life, but to find the pristine, unaltered precursors to life. On Earth, our planet's active geology and biology have completely overwritten the record of its earliest chemistry. We have no pristine samples of what the prebiotic Earth was like. The moon, lacking an atmosphere and geologic recycling, acts as a museum, and a sealed cave could be the most protected wing of that museum. The kinds of compounds scientists would be looking for include amino acids, the building blocks of proteins, nucleobases, the components of DNA and RNA, and polycyclic aromatic hydrocarbons, which are complex ring-shaped carbon molecules found all over space. The key is their state of preservation. In a cave, they might be found in a much more original state than in meteorites that have been heated and altered during their fiery passage through an atmosphere. A robot explorer designed for this task would be equipped with incredibly sensitive chemical analyzers. It might use a laser to vaporize a tiny spot on a rock or soil sample, and then use a mass spectrometer to sort and identify the molecules that are released. Finding a diverse set of such organics in a protected lunar cave would be a monumental discovery. It would prove that these building blocks can survive and be delivered in protected environments on airless bodies. This has direct implications for places like Mars, where similar lava tubes exist. If organics can survive for eons in a lunar cave, the odds improve that they could survive in a Martian cave, where conditions might once have been more hospitable to actual life. So, while the search on Mars is for signs of past life itself, the search in a lunar cave is for the uncontaminated raw materials that life, anywhere, might use. It's a step back in the chain of complexity. Furthermore, the cave environment itself might have allowed for some unique chemistry to occur. Without life to interfere, and with a steady, cold, protected setting, these organic compounds might have undergone slow, non-biological reactions over immense timescales. They might have formed more complex structures, or interacted with minerals on the cave walls in ways we haven't seen before. It's a natural laboratory for studying prebiotic chemical evolution, a process we can only simulate in labs on Earth. This line of inquiry also forces us to confront the concept of contamination in a new way. It's one reason why the early robotic missions will need strict sterilization protocols. If a robot trundling into the cave is covered in earth microbes, or even just traces of earthly organic molecules from our labs, it could completely confuse the findings. Discovering amino acids in a lunar cave would be huge, but only if we can be absolutely certain we didn't bring them there ourselves. This pushes planetary protection to a new level for the Moon, which has historically been treated as a dead world with less stringent rules than Mars. The potential for organics changes that calculus. The philosophical implications are deep, even if we stick to the science. Finding well-preserved organics in a lunar cave would underscore that the ingredients for life are not rare. They're common cargo in the solar system, splattered everywhere by impacts. It would suggest that any rocky world with similar protective niches, caves, subsurface pores, could have accumulated these ingredients over time. The difference between a world with life and a world without might then come down to other factors. The presence of liquid water for long periods, a stable energy source, and perhaps just the right sequence of events to assemble those ingredients into something self-replicating. The Moon had the ingredients delivered, and it even had volcanic activity and possibly liquid water very early on, but it lacked the size and geological longevity to sustain the process. It is a frozen snapshot of what might have been, or of what the early Earth's environment might have contained before life took over. For astrobiologists, this makes the lunar cave a unique and powerful control experiment. On Earth, biology is everywhere, making it hard to study non-biological organic chemistry in nature. In most of space, radiation destroys these compounds. The lunar cave offers a perfect middle ground, a natural, accessible setting where pure, ancient, abiotic organic chemistry might be preserved in a readable state. The pursuit of this knowledge will shape the instruments we send. It means including tools that can detect and characterize carbon-based molecules at very low concentrations. It means planning sampling strategies that prioritize very cold, shadowed regions of the cave floor, where volatiles and organics would be most stable. It might even mean designing sample return missions, where sealed tubes of cave soil are brought back to Earth for analysis in ultra-sensitive laboratories that no rover could ever carry. In the end, the search for organics in lunar caves is a search for our own chemical origins. It addresses the question, what was available on the early Earth? By finding a preserved collection of these materials on the Moon, we get a clearer picture of the starter kit that was present in our corner of the solar system. It moves the discussion of life's origins from pure theory into the realm of tangible, empirical evidence gathered from another world. So, while the robots will be looking down at the ground for signs of water and interesting rocks, they will also, in a very real sense, be looking for a reflection of Earth's own lost infancy, a chemical echo from a time before biology, preserved in the silent, dark vault of the Moon. This potential elevates the mission from pure exploration and resource assessment to a fundamental quest to understand the distribution of life's precursors in the cosmos. It is a long shot, but the payoff is so high that it absolutely justifies making it a key objective for the first brave machines that venture into the abyss. The possibility of finding pristine organic compounds, or any other untouched scientific treasure within a lunar cave, leads us directly into one of the most critical and complex debates surrounding their exploration, the dilemma of contamination. The moment we send a probe, or eventually a human, into that sealed environment, we irrevocably change it. This isn't just an academic concern, it's a practical and ethical problem that forces us to weigh our desire for discovery against our responsibility to preserve the very things that make the cave valuable in the first place. There are two sides to this contamination coin: forward contamination and back contamination. Forward contamination is the risk we take by sending our earthly microbes and organic materials into the cave. Every spacecraft, no matter how clean, carries a microbial biosphere. On the surface of the Moon, this isn't a huge concern because the harsh conditions of radiation and temperature are assumed to quickly sterilize any stray Earth microbes. But inside a protected cave, especially one that is cold and stable, the equation changes. It's conceivable that some hardy terrestrial bacteria, shielded from radiation by the spacecraft's own structure and then deposited in the cave's benign environment, could survive. They might not proliferate wildly without a food source, but their mere presence would contaminate the site. If, later on, we detect organic molecules or even ambiguous chemical signatures, we would face an impossible question. Are these native to the Moon, or did we bring them? This would ruin the cave's value as a pristine record. To mitigate this, any robotic mission destined for a cave would need to undergo sterilization protocols, similar to those used for Mars landers that search for life. This involves baking components in ovens, using harsh chemicals, and assembling the probe in clean rooms to reduce the microbial load to an absolute minimum. It adds cost and complexity, but for the first missions of pure science, it is considered essential. The other side is back contamination, which is the risk of bringing something potentially hazardous from the Moon back to Earth. For lunar caves, this risk is considered extremely low, as the Moon is not seen as a habitat for living organisms. However, the cave's role as a potential preserve of ancient organic chemistry introduces a slight nuance. While there is no risk of an infectious agent, there is a remote possibility that we could bring back a novel chemical compound, or a geological sample that behaves in unexpected ways in Earth's biosphere. This risk is deemed so minimal that it likely wouldn't prevent sample return, but it would mandate careful handling and analysis in secure facilities, much like the samples from the Apollo missions were initially quarantined. The real tension arises when we shift from robotic science to human exploration. Humans are the ultimate contamination vectors. We are walking, talking ecosystems, shedding millions of skin cells and bacteria every minute. A human entering a lunar cave would instantly and permanently pollute it with our biological and chemical signature. This creates a major conflict. Scientists would rightly argue that we must complete a comprehensive robotic investigation, including pristine sample return, before we ever allow a boot to touch the cave floor. Once humans are in, the environment's purity for certain types of scientific inquiry is gone forever. On the other hand, engineers and exploration advocates point out that these caves are the most promising sites for sustainable human habitation. The need to explore and utilize them for shelter and resources is a powerful driver. This leads to tough questions about prioritization and preservation. Do we designate some caves as scientific preserves, off limits to all but the most sterile robots, while others are open for human development? How do we decide? The criteria would involve the cave's specific scientific potential. Does it show signs of unusual volatiles or unique geology, balanced against its strategic value for base construction? Is it particularly spacious, stable and accessible? This is a new form of planetary zoning, and it requires international discussion and agreement. The protocols for human activity in a cave, should we choose to enter one, would also need to be strict. Astronauts would likely use the cave in a manner similar to how scientists treat sensitive archaeological sites or Antarctic dry valleys. They might establish a designated clean zone for sampling, using tools sterilized on Earth, and a separate operational zone for the habitat and machinery, accepting that area is contaminated. They would take extreme care not to track the contaminated regolith from their boot soles into the pristine areas. It would be a constant logistical challenge. This entire discussion falls under the umbrella of planetary protection, a set of guidelines established by the Committee on Space Research to prevent the biological contamination of celestial bodies. Historically, the Moon has been categorized as a low-priority body for protection, given its assumed sterility. The discovery of caves and the potential for preserved organics might prompt a re-evaluation of that category for specific, sensitive locations. It wouldn't mean treating the whole Moon like Mars, but it could mean creating special protected area designations for caves with high scientific potential. The ethical dimension is profound. We are on the cusp of becoming an interplanetary species, and with that comes a stewardship responsibility. These caves are not just empty holes, they're unique records of solar system history, undisturbed for billions of years. Do we have the right to alter them the moment we find them? Many argue that we have a duty to study them with minimal impact first, to learn what they have to teach us in their original state, before we transform them for our own use. It's the difference between visiting a library to read the books and immediately moving your furniture in to start living there. The knowledge gained from a pristine study could be irreplaceable. Furthermore, there is an argument for preserving some of these sites for future generations of scientists who will have even better tools and questions. We might not even know what to look for today. If we contaminate everything now, we close those doors forever. This debate mirrors those we have on Earth about wilderness preservation versus development, but with the added complexity of an utterly alien and irreplaceable environment. The solutions will require a blend of technology, policy, and international cooperation. Technologically, we can develop better sterilization methods and robotic proxies that are so capable they reduce the immediate need for human entry into the most sensitive spots. In policy, space agencies need to work together to establish clear guidelines, perhaps through the United Nations, defining how to classify and protect such sites. It's a test of whether we can explore expansively but thoughtfully, avoiding the mistakes of a colonial rush, where scientific and preservation values are secondary to exploitation. For the first missions, the path is clearer. The initial robots must be as clean as possible. Their data will tell us which caves are scientifically priceless and which are more straightforward empty volumes. That information will then guide the difficult choices about where humans should and should not go. The dilemma of contamination forces us to confront the dual nature of our ambition. We are both seekers of knowledge and builders of new homes. Balancing these impulses is perhaps the greatest non-technical challenge of the lunar cave era. It asks us to be not just explorers and engineers, but also careful curators of the solar system's ancient history. The way we handle these first pristine environments will set a precedent for how we treat all others, from the caves of Mars to the icy oceans of the outer solar system moons. It is about proving that we can expand our presence without mindlessly erasing the unique records of the cosmos in the process. The silent, dark caves of the moon have waited for billions of years. A little more time to plan our approach, to ensure we learn before we alter, is a small price to pay for the integrity of the story they hold. This careful, measured progression, from sterile robot to potentially contaminating human, defines the responsible pathway forward, ensuring that our inevitable footprint does not completely obliterate the priceless footprints of cosmic history that came before. The debate over contamination and preservation hinges on a crucial, unanswered question. Is the cave we found a solitary wonder, or is it merely the first discovered room in a vast hidden network? Before we can make informed choices about which caves to protect and which to develop, we need a map. We need to know what we're dealing with on a global scale. This drives the next great phase of lunar discovery, the cartography of the underworld, the systematic search for other entrances to the moon's subterranean realm. The immediate goal is straightforward: find more skylights. The method, however, is a multifaceted treasure hunt combining old data, new algorithms, and specialized orbital instruments. Scientists are now engaged in a massive rescanning of the entire lunar surface with a new set of eyes, specifically trained to look for the subtle signatures of a cave entrance. The primary tool remains the incredible image archive from the Lunar Reconnaissance Orbiter camera, but this time they're not just looking for the obvious deep black pits. They're applying more sophisticated image recognition software, algorithms that can detect slight linear depressions, chains of small pits, or subtle tonal variations that might indicate a subsurface void very close to the surface. They look for patterns. A series of collapses in a line could trace the roof of a long lava tube. They examine the rims of sinuous rills, those snake-like channels, searching for spots where the channel appears to vanish into a pit, suggesting it goes underground. It is a painstaking pixel-by-pixel examination of a world, but it's where the next big discoveries are most likely to emerge. Beyond visible light cameras, other instruments on orbiters provide critical clues. One of the most promising is radar. The LRO itself carries a radar instrument, but more powerful ground-based radar from Earth, like the Arecibo Observatory when it was operational, has also been used. Radar works by sending radio waves down and timing their echo. A solid surface returns one signal, but if the radio wave hits a subsurface cavity, it can create a distinct double echo, one from the surface and a second delayed one from the floor of the cave beneath. Analysing these radar echoes can not only suggest the presence of a void, but can also estimate its depth and size. This is a non-invasive way to see tens of meters below the dusty surface. Another powerful technique involves temperature. The Diviner instrument on LRO measures the thermal emission of the lunar surface. Skylights have a unique thermal fingerprint. During the scorching lunar day, the open pit radiates heat, but the shadowed interior remains cool. At night, the situation reverses. The cold surface cools quickly, but the cave interior, insulated by rock, retains a bit more warmth and radiates it back out. This means a skylight will appear as a cool spot during the day and a relatively warm spot at night compared to its surroundings. By mapping these anomalous thermal signatures, scientists can flag potential cave entrances for further investigation. A fourth, more subtle method involves gravity. Large subsurface voids actually create a tiny localized dip in the Moon's gravitational field. Orbiting spacecraft like NASA's Grail mission, which ended in 2012, mapped the Moon's gravity in exquisite detail. By combing through that data, scientists can look for places where the surface geology suggests dense rock, but the gravity measurement is slightly weaker, hinting at an empty space below. This technique is better for finding very large cavities and is often used in conjunction with other data to build a case. The ultimate goal of all this detective work is to create a catalogue, an atlas of potential subsurface access points. This isn't just a scientific exercise, it is a foundational planning document for the future. Each confirmed or highly probable skylight becomes a candidate for a robotic mission. The catalogue will allow us to prioritise which skylights are in the most scientifically interesting regions, which are near potential landing sites or other resources, which ones appear to lead into the largest, most stable cavities. This mapping phase will likely reveal that caves are not uniformly distributed. They will be concentrated in the ancient volcanic plains, the Maria. Some regions might be honeycombed with them, others might be devoid. Understanding this distribution is key to understanding the Moon's volcanic history. A cluster of skylights in a specific area might indicate a major lava flow channel with a particularly extensive tube system. Mapping these could literally chart the underground rivers of a 3-billion-year-old volcanic episode. The process is iterative and self-improving. Every time a robot mission confirms a cave at a location predicted by orbital data, it validates the prediction methods. It tells scientists your algorithm correctly interpreted that thermal anomaly as a skylight. This allows them to refine their search parameters, making the hunt for the next one even more accurate. Over time, what begins as a list of a few candidates could grow into a database of hundreds of potential sites. This transforms our perception of the Moon from a two-dimensional landscape peppered with craters into a three-dimensional world with a complex hidden topography. The subsurface becomes a domain in itself. We start to think in terms of potential connections. Could two skylights a few kilometers apart be entrances to the same continuous tube? Could there be branching networks, like the roots of a tree spreading under the plains? Answering these questions might require more than orbital data. It might require dedicated missions. One concept is a hopper probe that could visit multiple skylights in a region, deploying small sensors into each one to measure conditions and confirm connectivity through atmospheric pressure sensors or other means. Another idea is a network of seismic sensors deployed around a skylight. If a moonquake or an impact occurs, the way sound waves travel through the subsurface could reveal the shape and extent of the cavity. The cartography of this underworld is therefore a multi-decade project, blending remote sensing, robotic reconnaissance and theoretical modelling. It is a prerequisite for any serious long-term planning. You would not build a city on Earth without a survey of the land. We will not build a base on the Moon without a survey of its subsurface potential. This mapping effort also democratises access in a way. If caves are plentiful, then many nations and commercial entities could have access to a protected, resource-rich site, not just those who land at the limited polar or equatorial zones currently deemed most strategic. It opens up the entire lunar surface for consideration, as long as you can find your own front door. In practical terms, the teams doing this work are creating the equivalent of real estate listings for the Moon. Listing number 1, spacious subterranean volume, stable temperature, excellent radiation shielding, possible water views. The more listings they can confirm, the better the choices for humanity's first permanent address off-world. This systematic search, this patient cartography, is the unglamorous but utterly essential bridge between the first thrilling discovery and the era of routine exploration and settlement. It is the work of turning a miracle into a map, and a map into a menu of futures. Every new skylight identified is another option, another opportunity, another chapter waiting to be opened in the story of our species on the Moon. The orbital scouts are now surveying the land with a new question, not just what is on the surface, but what is beneath it. The answer will chart the course for the next century of lunar activity. Mapping those subsurface networks is the first step, but the ultimate driver for turning those maps into occupied territory will be economics. The idea of a lunar economy moves from science fiction to practical necessity. the moment we decide to stay for more than a few days. And the caves, with their protective qualities and potential resources, are poised to become the foundational hubs of this new economic activity. It's not just about finding a safe place to sleep, it's about identifying and utilising the materials around that safe place to build, power, and sustain everything we do. This is the concept of in situ resource utilisation, and it transforms the cave from a shelter into a potential industrial park. The most talked about resource is, of course, water ice. But let's broaden the view. The lunar regolith itself is a resource. Inside a cave, that regolith has been protected from solar wind alteration, which might make its chemical and physical properties slightly different, perhaps more useful for certain processes. It is rich in oxygen, silicon, iron, aluminum, and magnesium. With sufficient energy, you can extract breathable oxygen from the rocks. You can process the regolith to create construction materials. Imagine a cave housing a 3D printing facility that uses sintered lunar dust as its ink to fabricate tools, spare parts, or even structural elements for expanding the habitat. The cave provides the ready-made protected factory floor. Then there are the more speculative but high-value resources. The Moon's surface is known to contain traces of rare Earth elements, which are crucial for modern electronics and magnets. There is also helium-3, an isotope scarce on Earth but deposited on the lunar surface by the solar wind over billions of years. Helium-3 is a potential fuel for future nuclear fusion reactors, while mining helium-3 would likely be a surface operation due to how it is implanted. A cave base could serve as the processing and storage centre, protecting the valuable product and the sensitive equipment needed to handle it. The cave's stable environment is ideal for any kind of precision refining or manufacturing process that would be disrupted by the wild temperature swings and dust on the surface. But how would this mining actually work? It starts with prospecting. The initial robotic missions we discussed will be geological surveyors, sampling the cave floor and walls to create a detailed resource map. They will look for concentrations of useful minerals, perhaps veins in the cave walls that were formed as the lava cooled. They will definitely be hunting for any signs of ice deposits. Once a valuable deposit is identified, the next phase is extraction. For regolith, this might be relatively straightforward. Autonomous rovers with scoops or excavators could collect bulk material from the cave floor and transport it to a processing plant. For harder rock, you might need drilling and cutting equipment. For ice, if it's mixed with soil, a rover might collect the frozen dirt and deliver it to a heating unit that boils off the water vapour, which is then captured and condensed. All of this machinery must be designed to operate in perpetual darkness and fine dust that will get into everything, and with high autonomy because direct human supervision will be limited, especially in the early days. The processing plant itself is a major piece of infrastructure. It needs power, a lot of it. Solar panels are useless inside a cave, so power must be brought in from the surface. This could involve running cables down from solar arrays placed in perpetual sunlight on a nearby peak, or perhaps using nuclear fission systems placed safely outside or at the cave entrance. The energy is used to run crushers, heaters, chemical processors, and 3D printers. The output could be anything from ingots of metal and canisters of oxygen to slabs of construction material and bottles of water. This is where the cave's scale becomes an economic advantage. The vast interior volume allows you to set up an entire industrial chain in one location. You can have the mining area, the processing plant, the manufacturing workshop, and the storage warehouses all under the same protective roof, minimizing the need for risky surface transport. The products created then feed the growth of the base itself and can be sold or traded. Oxygen and water are life support commodities. Rocket fuel produced from water is a transportation commodity. Construction materials are a real estate commodity. A cave base that can produce these things achieves a level of self-sufficiency that reduces its crippling dependence on supply ships from Earth. This turns a cost centre into a potential profit centre. It enables a broader economic model. Perhaps companies will pay to have their experiments or manufacturing processes conducted in the stable cave environment. Maybe the processed fuel will be sold to other lunar missions, turning the cave base into a gas station for the cislunar economy. The helium-3 or rare earth elements, if economically viable to extract, could be exported back to Earth, though the launch costs from the Moon are far lower than from Earth, making this more plausible. The cave itself, as a secured ready-made volume, has real estate value. Agencies or companies might pay for the right to develop a particular cavern. This embryonic economy will start slowly, driven by government investment in basic infrastructure. But the goal is to create a multiplier effect. The initial investment in a mining and processing capability lowers the cost of subsequent expansion, which attracts more activity, which creates more demand for local services and products. It's the same pattern seen in every frontier settlement in human history. The lunar cave offers a unique advantage over historical examples. The frontier town is already built by geology. We just need to equip it. The challenges are immense. The machinery must be incredibly reliable because breakdowns are hard to fix. The dust is a constant menace for moving parts. The economics must eventually close. The value of the resources produced must exceed the astronomical cost of getting the equipment there in the first place. This is why water is the key. Rocket propellant derived from lunar water could pay for itself by enabling cheaper exploration beyond the moon, saving the even greater cost of launching all that propellant from Earth's deep gravity well. So the economic case for lunar caves is fundamentally about leveraging local resources to break the chain of terrestrial supply. It is about creating a system where the moon pays for its own development, or at least significantly subsidizes it. The cave is the ideal locus for this activity because it provides free radiation shielding, thermal stability, and meteorite protection for all this expensive infrastructure. Investing in a surface factory requires building its own fortress. Investing in a cave factory means the fortress is included. This makes the economics slightly less daunting. In the long run, a thriving lunar economy based on in situ resources is the only path to a permanent, growing human presence beyond Earth. The caves aren't just a good option within that plan, they're emerging as the logical centres of it. They offer the trifecta: safety, resources, and space. The mapping missions will find the locations, the prospecting robots will identify the wealth. And if the numbers work, the caverns will change from silent, empty tombs of ancient lava into the bustling, illuminated workshops of humanity's first off-world industrial revolution. It all starts with seeing the rock not just as a shield but as a source. That economic potential, the vision of mining and manufacturing, all hinges on a single critical requirement. People need to live there. And not just in temporary camps, but in habitats designed for long-term residence, where crews can be healthy, productive and sane for months or years at a stretch. Designing such a habitat inside a lunar cave is a completely different engineering discipline than building for the surface. It's not about creating a sealed bubble against a lethal exterior. It's about creating a comfortable interior within an already protective but utterly alien shell. The fundamental shift is in the pressure differential. On the surface, a habitat module is like a submarine in space. Its walls must withstand the immense force of 1 atmosphere of pressure, inside pushing out against the perfect vacuum outside. This demands incredibly strong, rigid structures, often with complex geometries to manage stress, which are heavy and expensive to launch. Inside a lava tube, the external environment is also a vacuum, but it's an protected vacuum. The vacuum is inside the cave, which is itself sealed off from the surface by meters of rock. This might seem like a minor distinction, but it changes everything. The primary threat of a sudden decompression from a micrometeorite strike is virtually eliminated. The habitat walls no longer need to be the primary barrier against cosmic hazards. This allows for much more flexibility in design. Engineers could use lighter materials, they could employ inflatable structures, which are compact for launch, and then expand to provide large living volumes. An inflatable habitat inside a cave is incredibly appealing. You land a packed, rugged cylinder, lower it into the cave, anchor it to the floor, and then inflate it. The cave walls protect it from debris and radiation, so the fabric itself doesn't need to be armoured. It just needs to hold air. The rock around it provides the structural backup. This is a huge mass savings. The anchoring system becomes crucial. How do you secure a large, potentially lightweight structure to the irregular rocky floor of a cave? One concept involves a network of anchors drilled or bolted into the basalt, with tethers or a rigid frame that holds the habitat in place, preventing it from drifting or shifting. The floor itself would likely need some levelling. Perhaps a robotic rover could clear a pad of the largest boulders and spread a layer of processed regolith to create a flat foundation. Inside, the layout can take advantage of the cave's scale. On the surface, every cubic metre is fought for. In a cavern, you have volume to spare. You could design vertically. Imagine a multi-story habitat with living quarters on one level, labs and workshops on another, connected by staircases or ladders. This use of vertical space is a luxury impossible in most surface module concepts. It allows for a feeling of spaciousness and separation of functions that is vital for mental well-being on long missions. You could even have a central atrium or common area that gives a sense of openness, reducing the feeling of claustrophobia. The cave environment also offers unique solutions for life support. Thermal management is a prime example. On the surface, managing the wild temperature swings requires active heaters and coolers with large radiators to dump heat. In the cave, the temperature is constant and cold. The habitat will generate waste heat from people, electronics, and machinery. This heat can be managed passively by radiating it to the cave walls. Engineers might design the habitat with its outer surface in contact with the rock, using the immense thermal mass of the cave as a heat sink. Or they could use heat exchangers that transfer excess heat to the surrounding rock. This drastically reduces the complexity and power requirements of the thermal control system. Another system is atmosphere revitalization. You still need to scrub carbon dioxide and provide oxygen, but the cave offers a stable environment for these chemical processes. There's even a speculative idea of using the cave itself as a part of the life support system in a far future large-scale settlement. By sealing off a large section of the cave and filling it with a breathable atmosphere, you could create a truly vast shirt-sleeve environment. The engineering challenges of doing that are monumental. The cave is not a perfectly sealed vessel, and its porosity would lead to gradual gas loss. But it illustrates the paradigm shift in thinking. Instead of building a small can to live in, you're conditioning a geological space. Lighting is one of the biggest design challenges and opportunities. There is no natural light cycle. This is a serious problem for human circadian rhythms, which rely on light cues to regulate sleep, hormone production, and overall health. The habitat's lighting system would need to artificially simulate a 24-hour Earth day. This could be done with full-spectrum LEDs that change colour temperature and intensity, bright and bluish during the day and dim and reddish at night. But the designers could go further. They could create light wells, channels or fibre optics that pipe actual sunlight from collectors on the surface down into the cave, providing a genuine day-night cycle for at least a portion of the base. This would have immense psychological benefits. The visual environment is also key. The interior design would need to combat the sensory deprivation of being in a sealed box inside a dark hole. Use of colour, imagery of nature, virtual windows displaying Earth scenes or simulated outdoor environments, and even carefully designed interior gardens or greenhouses would be essential for crew morale. The connection to the cave itself could also be a feature. Perhaps one wall of a common area could be a reinforced transparent panel, allowing inhabitants to look out into the illuminated cavern, giving them a sense of place and connection to the lunar environment they're exploring rather than complete isolation from it. Sound is another factor. The cave is silent. The habitat will be filled with the constant hum of machinery. Acoustic design to dampen noise and create quiet spaces for rest and concentration will be important. The infrastructure connections are also unique. Power, as mentioned, likely comes from the surface. Cables would run down from solar arrays or a nuclear power source. Communication cables would follow the same path. Water and waste management systems would be self-contained, but could be scaled up more easily given the space. Waste processing for recycling water and air might be housed in a separate module within the cave, away from the main living areas, again made possible by the ample room. Safety systems have a different focus. The primary risks shift from external puncture to internal fire, equipment failure, or medical emergency. Escape plans are complex. You cannot just run outside. You would need a pressurized rover or ascent vehicle always on standby, capable of climbing out of the skylight, or using a dedicated elevator shaft to reach the surface and a pre-positioned lander. Multiple redundant airlocks and safe haven compartments within the habitat would be standard. The design process for such a habitat is inherently interdisciplinary. It requires geologists to understand the rock mechanics of the cave, architects to design for human well-being and confinement, engineers to build the systems, and psychologists to inform the layout and aesthetics. It gives rise to a new field, subsurface space architecture. This isn't just about adapting existing space station modules. It's about creating a new archetype for living on other worlds, one that leverages the natural infrastructure provided by the planet itself. The first such habitats will be modest, perhaps a single inflatable module for a crew of 4, focused purely on basic science and proving the concept. But the blueprint they establish, the lessons learned about anchoring, thermal integration, lighting and psychology, will define the expansion into larger, more permanent settlements. The cave habitat represents the ultimate goal of the entire endeavour, a place where humans don't just visit but truly live, work and build a future, all within the enduring shelter of a bubble of rock that has waited billions of years for inhabitants. It transforms the cave from a destination into a dwelling, completing the journey from discovery to home. The vision of a safe, spacious habitat within a lunar cave is compelling, but it rests on a foundational assumption that the cave is a stable, predictable environment. The reality is that we are considering moving into a geological structure that is billions of years old and that we have never directly observed. For all their promise, these caverns come with a unique and serious set of risks and unknowns, a dark side to the dark void that we must honestly confront before any human ever considers calling on home. The first and most obvious concern is structural integrity. Yes, the lower gravity allows for wider spans, and the rock has held for eons. But what is its current state? The cave roof has been subject to billions of years of thermal cycling from the surface above, albeit dampened. It has experienced moonquakes, however mild. It has taken micrometeorite impacts on its outer surface. Could there be hidden cracks or stress fractures that are not visible from a preliminary robotic scan? When we start activity inside, vibrations from machinery, pressure changes from habitat systems, or even just the repeated movement of heavy rovers, could we trigger a localized collapse? A falling piece of basalt the size of a car is a catastrophic event in a pressurized habitat. Before settlement, we would need detailed seismic and ground-penetrating radar surveys of the entire ceiling and walls, looking for weaknesses. We might even need to consider active stabilization measures, like bolting or meshing certain sections, which is a whole new category of construction in a vacuum. Then there is the dust. We talk about lunar regolith on the surface being a nuisance, but the dust inside the cave could be a different and possibly worse beast. On the surface, solar radiation charges the dust particles, making them stick to everything. Inside the cave, shielded from that radiation, the electrostatic properties might be different, but that doesn't mean benign. This dust has never been gardened or weathered. It might be sharper, more angular. It would be stirred up by any activity and would settle on every surface, including the critical seals of habitat airlocks, the lenses of cameras, and the mechanisms of robots. If it is less electrically charged, it might not stick as tenaciously, but it would float longer in the vacuum before settling. In a habitat, tracking this dust in would be a major concern. Its abrasive qualities could damage equipment, and if inhaled, its sharp glass-like particles could cause serious lung damage, a condition space medics call lunar hay fever. We know little about the exact properties of this subsurface dust, and characterizing it will be a top priority for the first robotic missions. The complete and utter darkness is more than an inconvenience. It is a fundamental operational hazard. All navigation and work are entirely dependent on artificial light. A power failure that kills the lights plunges everything into a blackness so absolute it is physiological and psychological shock. Redundant power systems and lighting are a must, but so are redundant navigation systems. If a rover's cameras fail, how does it find its way back? If an astronaut becomes separated from their team and their suit lights fail, they are in unimaginable peril. The environment offers no visual cues. You cannot see the sun to orient yourself. Every mission, robotic or human, would require multiple fail-safe methods of navigation, inertial systems, detailed pre-mapped LiDAR routes, and physical markers or beacons placed along paths. The terrain itself is a major unknown. From orbital data we might see a smooth floor, but that smoothness is relative. It could be a field of loosely piled boulders ready to shift under weight. There could be hidden crevasses or holes partially filled with dust, creating treacherous traps. The first robots will need to be agile and equipped with hazard detection systems to map this terrain in high detail before we ever walk on it. Then there are atmospheric risks, or more accurately the risks from what little gas might be present. The cave is a vacuum, but it is not necessarily an empty one. Over billions of years, radioactive decay in the rock could have released small amounts of radon gas, a radioactive element that can accumulate in enclosed spaces. On Earth, radon in basements is a health hazard. In a lunar cave habitat with a sealed atmosphere, radon seeping from the walls could concentrate to dangerous levels, requiring monitoring and filtration systems. Other volatile substances, if present, could also pose risks if disturbed. Drilling into a wall or heating the floor to extract water ice could potentially release pockets of trapped gas, causing a sudden, localized pressure change, or even a blast of toxic material. The dependency on artificial systems becomes a single point of failure in a new way. On the surface, if your main habitat fails, you might retreat to a lander or a pressurized rover. In a cave, your exit is a vertical shaft or a long, dark tunnel. All systems for life support, lighting, communication, and most critically ascent must work flawlessly. The elevator or winch system that connects the cave base to the surface is a literal lifeline. Its failure would strand people underground with no easy way out. This necessitates multiple redundant egress methods, which complicates design and increases mass. Finally, there is the psychological risk of such an environment. Living on the surface, you can at least see Earth, see the stars, see the landscape. You have a connection to the outside. Living in a cave, you're completely divorced from the cosmos. You're in a human-made bubble of light inside a mountain of stone. The sense of isolation and confinement could be profoundly more intense than in a surface habitat with windows. Countermeasures like virtual windows, expansive interior design, and scheduled communication with Earth are not luxuries. They're critical mental health infrastructure. All of these risks are not deal breakers, they're engineering problems, but they underscore why the robotic reconnaissance phase is non-negotiable and must be thorough. We cannot just lower a habitat into the first hole we find. The first machines will be risk assessment scouts. They will map the structure with seismic sensors, thumping the ground to listen for hollow spaces. They will sample the dust and test its properties. They will monitor for any trace gases. They will test the stability of the floor and walls. They will practice anchor deployment for future habitats. Every piece of data they send back will be used to build a risk profile for that specific cave. Some caves will be deemed too unstable or risky. Others will present manageable challenges. This process turns the unknown into the known and the dangerous into the manageable. It is the essential work of turning a wild frontier into a potential home site. Embracing these caves means embracing their complexities, not just their benefits. The path to safety is through the meticulous, patient work of characterizing every shadowy corner and understanding every hidden threat. The robots will blaze that trail, their sensors acting as our eyes and hands in the dark, ensuring that when humans finally follow, they're stepping into a calculated risk, not a blind gamble. This cautious step-by-step approach is what separates sustainable expansion from reckless adventure. The caves hold immense promise, but that promise is unlocked only by first respecting the profound unknowns that lie within their ancient silent depths. Confronting and solving those risks on the moon is not just about making lunar bases possible. It is about creating a template, a playbook, and a set of proven technologies for the next, and arguably more important, destination, Mars. The paradigm of subsurface living, which the lunar caves are forcing us to develop, is not a lunar-specific idea. It is, in many ways, even more applicable and critical for the Red Planet. Mars presents a similar set of surface horrors: radiation, dust storms, and extreme cold, but on a larger scale and with the added challenge of immense distance. The lessons we learn from accessing, assessing, and occupying lunar caves will directly and powerfully translate into the first sustainable human presence on Mars. Think about the similarities. Mars is covered in evidence of past volcanic activity. Orbital images show clear features that look like skylights, collapsed segments of what are likely lava tubes of monumental proportions. Due to Mars' lower gravity compared to Earth, though higher than the Moon's, these tubes could be even larger than their lunar counterparts. They are the ultimate ready-made shelters. But Mars adds its own complexities. A thin atmosphere that still poses challenges for landing and creates planet-wide dust storms, and the haunting possibility of past or even present subsurface life. A Martian cave base would offer all the same primary benefits as a lunar one: shielding from cosmic and solar radiation, protection from the micrometeorites, though the atmosphere helps with that, and a thermally stable environment that avoids the 100-degree swings of the surface. It would also offer a crucial defense against the global dust storms that can blot out the sun for months, crippling solar-powered surface operations. A cave base could be powered by compact nuclear sources, independent of the weather, so the strategic value is identical, but the stakes are higher. The moon becomes our testbed, our analogue site. It is close enough that we can send robotic missions relatively quickly and cheaply compared to Mars. A mistake or a failure on the moon is a tragedy, but it is days away in communication time and weeks or months away in travel time for a replacement. A similar mistake on Mars, with a 20-minute communication delay and a 2-year wait for the next launch window, could be catastrophic for a mission. Therefore, we need to work out the kinks nearby first. The robotic systems we're developing for lunar caves are direct prototypes for Martian cave explorers. The autonomous navigation in complete darkness, the LiDAR mapping, the communication relay systems, the mechanisms for descending into skylights, all of this will be tested and perfected on the moon. By the time we send a mission to a Martian skylight, the core technology will have a proven track record millions of miles away on a similar, airless body. The operational experience will be invaluable. How do you manage a robotic cave exploration campaign from Earth with a significant time delay? We will develop those protocols on the moon, where the delay is only a few seconds, before applying them to Mars with its 20-minute lag. The human factors we learn about in lunar caves will inform Martian habitat design. How do people psychologically respond to living underground for a year? What lighting schemes work best? How do you maintain team cohesion and mental health in such an environment? A long-duration lunar cave mission, lasting 6 months or a year, would be the closest possible analogue to a Martian surface mission without actually going to Mars. The data on crew health, habitat systems performance, and emergency response in a sealed subsurface environment would be gold for Martian mission planners. Furthermore, the moon allows us to test the in-situ resource utilization technologies that are even more critical for Mars. If we can mine and process water ice from a lunar cave, we prove the concept for doing the same on Mars, where water ice is also believed to exist in subsurface layers and caves. The machinery might need tweaking for different soil chemistry and gravity, but the core processes, excavation, heating, condensation, will be the same. The economic model of using local resources to create fuel and air is the only model that makes a Martian settlement conceivable. The moon is where we work out that model's practical details. There is also the profound scientific synergy. The search for organics in pristine lunar caves, as we discussed, is a direct rehearsal for the search for signs of life in Martian caves. The planetary protection protocols we establish for the moon, how to explore a pristine subsurface environment without contaminating it, will be the strict baseline from Mars, where the possibility of life, however faint, demands even greater caution. The instruments we develop to detect trace organics on the moon will be flown to Mars. The moon is the dress rehearsal for the most sensitive astrobiological investigation in history. This transferability of technology and knowledge makes the lunar cave program not a diversion from Mars, but the most efficient possible path to it. It turns the moon from a destination into a workshop. Every robot that rolls into a lunar skylight is training for Mars. Every sensor that analyzes lunar cave dust is calibrating for Martian regolith. Every structural bolt tested in basalt is informing the anchoring systems for Martian habitats. The paradigm shift is also conceptual. By successfully establishing a cave base on the moon, we shatter the mental model that planetary surfaces are the default place to live. We prove that the subsurface is not a last resort but the prime real estate. This change in perspective will fundamentally shape all future mission architectures for Mars. It will redirect engineering talent and resources towards subsurface solutions from the very beginning, rather than as an afterthought. The public and political will to go to Mars can be bolstered by clear, step-by-step demonstrations on the moon. Showing a functioning, growing habitat in a lunar cave makes a Martian one feel less like science fiction and more like the next logical step. It provides a visible, tangible milestone on the road to the Red Planet. In essence, the lunar caves offer a unique gift, a nearby, accessible, and reasonably forgiving environment to develop the tools and techniques we need to survive in the most unforgiving environments imaginable on other worlds. They are the training wheels for becoming a cave-dwelling species across the solar system. The technologies matured there will not only enable lunar villages, but will form the core systems for the first Martian settlements. The experience gained there will save lives, time, and trillions of dollars on the longer journey. So while the moon is the immediate goal, every advancement in exploring its hidden recesses is a direct investment in the future of humanity on Mars. The cave we crack open on the moon is a doorway that leads, inevitably, to the caves of Mars and beyond. It establishes a blueprint for living on any airless or thin-atmosphere rocky world, turning our nearest celestial neighbour into the ultimate proving ground for our interplanetary future. This strategic link elevates the entire lunar cave endeavour from a fascinating geological side quest to a central pillar of humanity's deepest space exploration ambitions. The lessons written in the dark silence of the lunar underground will be the first chapters in the manual for surviving on the Red Planet. That step-by-step progression from the moon to Mars underscores a final, overarching point. This single discovery of an accessible cavern does more than just add a new location to our maps. It fundamentally rewires our understanding of the moon as a world. It forces a comprehensive rewrite of the manuals, the textbooks, and the strategic playbooks. For centuries, the moon has been viewed through two primary lenses, as a dead, geologically static orb, and as a surface to be crossed. The cave discovery shatters both those notions, introducing a third transformative dimension, the subsurface as a domain. We can no longer think of the moon as merely a landscape of craters and plains. We must now conceive of it as a world with an interior architecture, with hidden volumes and potential networks. This shifts its entire scientific and exploratory identity. In academic terms, textbooks on planetary geology must now include dedicated chapters on subsurface processes and preservation on airless bodies. The old story of the moon cooling and solidifying into a quiet tomb is incomplete. It now must include the legacy of its volcanic fervour, not just as surface stains, but as intricate hollow structures beneath. These structures become active elements in the moon story, not relics. They are places where chemistry was protected, where temperatures were stabilised, and where a record was kept. This turns the moon from a passive subject of study into an active archive. Similarly, engineering manuals for space architecture are being redrafted. The previous assumption was that habitats must be built up from the surface, designed as fortresses. Now, a parallel track exists. Habitats can be fitted into natural pre-existing shelters. This requires new standards for assessing geological stability, for anchoring in native rock, and for integrating life support with a planetary mass. A new engineering discipline is emerging from this discovery. For mission planners and strategists, the calculus of where to go has been upended. For decades, the discussion oscillated between the lunar poles, with their water ice, and the equatorial regions, with their easier landing and warmer temperatures. The cave discovery adds a powerful third vector, depth. The question is no longer just latitude and longitude, it's also how far down. A promising site is now evaluated not just for what is on its surface, but for what might be beneath it. This democratises lunar real estate in a fascinating way. A seemingly boring mid-latitude plain might sit atop a priceless cathedral-like cavern, making it more valuable than a tricky-to-reach polar crater. It forces a global reassessment of every planned landing site. The very definition of resource expands. Before, resources were what you could scoop from the surface or detect in shadowed craters. Now, the resource includes the void space itself, the protected volume. This is a non-consumable permanent resource. You don't use it up, you occupy it. This changes economic models. The value of a plot of lunar land is now tied to its subsurface rights, much like property on Earth can have mineral rights. This will inevitably lead to new legal and policy frameworks for off-world exploration and settlement. The psychological and philosophical relationship between humanity and the moon undergoes a subtle but profound shift. The moon has always been an other, a distant, harsh, and unyielding destination. The cave, with its promise of shelter, makes it feel less alien and more habitable. It suggests the moon isn't just a hostile place to endure, but a world that can, in its own way, provide for us. It becomes a partner in the endeavour, offering its own geological solutions to the problems it presents. This humanises the moon. It transforms it from a stark, luminous target in the sky into a place with nooks and crannies, with insides, with potential homes. It feels more like a place and less like a postcard. This is crucial for garnering public and political support for sustained exploration. People can envision living inside the moon in a way they might not envision living on its radiation-blasted surface. The discovery also redefines the timeline and pace of exploration. Previously, establishing a permanent base was a distant marathon project of hauling massive amounts of material. Now, there is a potential shortcut. Find the right cave and you have a head start. This doesn't make it easy, but it makes the goal feel more tangible and achievable in a shorter time frame. It provides a clear, compelling first step for permanence. Establish a foothold in a cave. This can accelerate plans and attract investment by presenting a more defined and de-risked path. Furthermore, the Moon's role in the broader space ecosystem is elevated. It is no longer just a testing ground for Mars hardware in a generic sense. It becomes the specific testing ground for subsurface living and exploration technologies. Its value as an analogue increases exponentially. Every agency and company with eyes on Mars will now look to the Moon not just for gravity and proximity, but for its caves. This consolidates the Moon's position as the indispensable stepping stone. Finally, the discovery redefines the nature of the mystery. For ages, the Moon's mysteries were all surface level, the origin of its craters, the composition of its rocks. Now, the greatest mysteries may be hidden in the dark. The questions have moved underground. Are there accessible volatiles, preserved organics, extensions that connect for miles? This renews scientific interest and ensures that lunar exploration will remain vibrant and discovery-driven for decades to come. It adds a layer of intrigue and wonder that was beginning to fade after the Apollo era. In the end, the confirmed lunar cave is more than a geological feature. It is a key that unlocks a new way of thinking. It challenges our categorization of the Moon as a simple dead world. It introduces complexity, opportunity and depth, both literal and figurative. It forces every related field, geology, engineering, law, psychology and strategy, to adapt and evolve. It marks the transition of the Moon from a two-dimensional symbol in our sky to a three-dimensional world in our future. The chapter titled The Dead Moon is closing. The new chapter yet to be fully written is The Living Moon, a World with an Interior. And that changes everything. This single hole in the ground is not an end point. It is an intellectual and exploratory Big Bang, from which a new universe of possibilities rapidly expands, reshaping our relationship with our closest celestial neighbour from one of distant observation to one of potential intimate inhabitation.